have like question, you can just like raise it to me and we can discuss it. So don't need to feel shy. So my name is Thien, but sometimes you may know better by my like handle on GitHub or like Discord with Beginners. Yep. So actually, I gave a very similar talk to the Kudamot Discord group last year. So this one will be mostly similar, but I gave some updates about the new thing that we saw the past year, like the DeepSeek and FP4. So yeah. So let's just go straight into it. So just a bit of recap. So most of the time when we talk about quantization, people think about post-training quantization. It means that once we have trained a model and then we quantize it so that it runs faster, or maybe it's just like it's a smaller model. And the typical task will be like the weight only. So it means that you only quantize the weight. During the forward pass, you do quantize the weight and do the normal matrix multiplication. And this will be like dynamic activation and weight quantization. So during the forward pass, you will also quantize the activation. Then you can do the like in a map mode or like FTA map mode. And there also like static activation quantization. I think this one is more like for CNN in the past. For right now, for transformer, usually people don't do static activation quantization because it has some accuracy issues. Yep. So this is just a basic recap for the post-training quantization. But when we go into the training world, right, they are much more complicated. Usually we have like another step about the backward pass and also the optimizer step. So the thing is, we can use quantization or we can use low bit actually for every step of the training process. So let me see here. All right. Yeah. And you can see in this below here, I put like a diagram of the memory footprint of what's happening during like one forward pass backward and the optimizer step. So you can see during the forward pass, usually you have build up the activations. And then during backward, you will free up the activations memory and but you will be up gradient memory. And the optimizer step will use the gradient to do the way update. So that's why it's going down here. And the model parameters and optimizer states are like the static VRAM usage because they are like the same during the training. Yep. So the goal of using low bit or like quantized stuff, it's basically just to save memory and also to make things go faster because on modern GPUs, usually like in a MAMO or like FK MAMO are much faster than just like BF60. So this will be just the overview of what we can do across the training stack. So the first thing I will go into will be low bit optimizers because I think this will be like the easiest, most straightforward. So this okay, and maybe I just skip this part. Maybe I just focus on this table here. Right. So laser pointer. So this table here, right? So why we want low bit optimizer, right? So if we go back to the previous page, you can see that actually the optimizer state usually occupy twice the amount of memory as the model parameters. So that's huge. Especially for LLM nowadays, right? LLM nowadays are huge. So if we can just quantize the optimizer state, we don't even need to quantize the model weights. We can already save a lot of memory. So for example, for an 8 billion model, right? If we start the optimizer state in FP32, it will be 64 gigabytes. But if we quantize down to like, for example, 4 bit, that will be only 8 gigabytes. So that's a huge amount of savings. So I think this is very useful. Like this will be like the first thing you should try when you want to do like introducing low bit into your training stack. So I think I will go this over quickly. So the standard optimizer will look like this, right? So you have like input to the optimizer will be the parameter, the gradient, and the optimizer state, and then it use some kind of equations, and then it calculate what should be the new parameter and new optimizer state. So it will update that. So that's why you can see I have the two arrows for the parameter and optimizer state, but for the gradient it's only once because actually you optimizer doesn't upgrade the gradient. It just take the gradient in and do some calculations. And this calculation will depend on like what, whether you have SGD or you have other. So the only difference when we are doing with low bit optimizers is that we are inserting this the quantized operation and the quantized operation in the optimizer state. Yeah. So before doing any optimizer logic, then we just dequantize the optimizer state, and then once the optimizer logic is finished, we just quantize it back. Yep. I think I will skip this part here. So actually, I also implement some of the low bit optimizers in torchao. So you can see here, but I think we're not focusing too much on this one here because the idea is pretty straightforward. All right. So any one of you have questions regarding low bit optimizers? So if we don't, I will just move on to the next part. So this will be more exciting part, I would say. So so now we are entering the realm where we try to use low bit for the parameter weight itself. So if we want to just do the recap of like doing all this kind of like low bit training, right? If we look at FP16 and BF16, it's actually a form of low bit training, if you think about it, because actually we still keep the model weights in FP32, and then we just dynamically cast the weight into like BF16 or FP16 during the forward pass as well as the backward pass. So that's why I also want to frame it as doing low bit training in this case. And then we also have the full FP16 and BF16 training. So in this case, actually, we don't have an FP32 weights, and we just keep the 16-bit weights for weight update. And actually, this will have some issues, and then I will show them to you later. And nowadays, Q low rate is also an important kind of like fine tuning. So that's why I also put it here. The idea is that once we have the pre-trained weights, we can quantize them. And we only need to train the high precision of the much lower weights, the A and B matrix. So usually these are much smaller than the base weights here. And so that's why we can keep this in high precision and keep the base weight quantized, which is much smaller. Yep, I think this one should be FP32 because if you have BF16, you have the same problem as the full BF16 training. Okay. So so what's the problem if we are just using the low bit weights for training, right? The biggest problem is the weight updates under flow. So this is the general equation of the optimizer step. So you have this one will be the current parameter, and then this one will be like whatever the optimizer calculates, like tells you how should you update the parameter, and then you scale by the learning rate, then you subtract it from the parameter, and this will be the new parameter. So the problem is that what if this update, right, it's too small compared to the current weight? And it means that this won't be updated at all. So just to give you a very simple example, imagine if you were using int8, right? And then we're using int8 for the weight parameter. And then somehow we calculate the update to be 0.1. So, or maybe it should be negative 0.1 or whatever. So if we add them or subtract them from the one right here, right? And we round down to the nearest integer, it will still be 1. So it means that our training will be stuck at this point and we can't do anything. So this is the biggest problem with using low bit for the weight during training. So okay, maybe I switch to this. So okay, yeah. So this one just to illustrate what I have. So just talk just now. So this one I make a small demo using PyTorch. So let me see here. So here we have a number 10, right? And I start that using int8. And then imagine if I just keep adding 0.2 to it, because of the rounding, right? I actually will never get something larger than 10 because of the rounding. But imagine this will be the optimizer update, and we will expect that to be like the the total of number of update times this change, right? So we want it to be 30, but actually it becomes only 10. So this is a big problem for us. And okay, okay, before we talk about that, okay, I just want to. Oh, I didn't have a one for BF16, but uh, it's all right. Okay, maybe go back to the slides. Okay, I thought I did a one for BF16, but so okay. So what we can do for this one? So one of the interesting techniques is called stochastic routing. So the basic idea is that we should route towards the direction that it's closer to us. So in terms of probability, so example on this number line here, we have like this will be route down. Let me get the laser pointer. So we have this one here route down, right? If we go to the floor function, and this one will be routing up. So the floor function plus one. Yeah. So for example, on this number line, if we are closer to the routing up, right, we should want it to route up with a higher probability. And the idea is that if we do this like randomly, right, the expected value will be equal to the actual value itself. So it means that even if we have, for example, like 1 plus 0.1, right? It means that there will be 10% of the time we will route up to 2, and then 90% of the time we will route down to 1. So imagine like we have a big network, you have a lot of numbers. So it means that uh 90% of the weights will be routing down, and 10% of the weight will be routing up. So it means that the model is still going somewhere. And on average, that should be going into the correct direction. So that's good. So just want to illustrate the idea of stochastic routing in this notebook here. So just gonna run this. So so the idea is very simple, right? So basically that's what I said. So for example, if we generate a random number between 0 and 1, right? We want the so it means that this the probability of the random number uh, being smaller than the distance from the routing down. I feel like when I say that it doesn't make much sense, but I think it's clearer when you look at this visualization. Yep, and then just believe that this, just convince yourself that this equation is doing what we expect, and then if we can run this multiple times, so you can see that it's kind of oscillate around the 30, which is what we expect it to do correctly. Okay. Yeah, I think sometimes it will go very far off, but like on average, it should be close. Yep. Um, So even though I illustrate the idea for in8, right? Actually, even BF16, you have actually the same problem. So, oh, you're right. I have the demo for BF16 here. So for example, I have a number 200 in BF16, right? And then I keep adding one to it. You can see it will stuck at 256 because actually you need to add two to it to get to the next number. So if I do like this, 256 plus 1, you see that it will be rounding down, but if I plus 2, it will be round up. Yeah. So there are gap between the BF16 here from 256 to 258. So actually you will get even the same problem for BF16. And that's why actually when you're doing full BF16 training, having some stochastic rounding actually helps a lot. And I think I have some results here, so maybe I can show you all. So this one, it's already merged to torchao. So actually, right now you can also already use I call this like Adam Adam BF16 with stochastic routing. So yep, so this is how you can use it if you want. So yeah, you can just add this flag and it will work. So I'm just gonna show you the result. I think that's more exciting here. So in this one, I purposely use a very small learning rate so that I want the weight update to be small. And this is the loss curve. So as you can see in this one, actually, because they are overlapped, you can see the value here, right? The full with stochastic routing, and this one with the automatic mixed precision. So that's the standard way of doing mixed precision training on single GPU, right? You see, actually they are identical. That's why they overlap, and then you can't really tell the difference. But you can see the value of 3 point something. They are the same. And then the one that I don't use any stochastic routing, right? You can see that it's much different. The loss doesn't go down because of the problem I said just now. Because you have a too small weight updates, so it's not going anywhere. It's stuck in that position. Yep, and then you can see the benefit of that. So just by using a full full BF16, then you can save a lot of VRAM here. So you see the full with stochastic routing, you save 4 GB in this case. Right, 4 GB. Okay, and yep, and then you see you get very good speed. So it's even much. So using BF16 full BF16 is actually slightly faster than mixed precision because actually you don't need to do the casting, the dynamic casting from FT32 to BF16. So that's even better. So yeah, so I think that's kind of this one. This would be like a very small step up from the normal mixed precision, and I think if you can afford it, you should do it. So yes.
I have one question here. So this your attention would be in what precision, like BF16, in this
Uh,
like flash attention or something similar to that?
yes, it will be still in BF16. So this
Right.
one, it's only changing the way updates. It doesn't change anything in the forward pass and the backward.
Okay. Okay.
Yeah.
Sounds good. Thank you.
Yeah. So only changing the optimizer. Okay, let's go back here. So this is just full BF16 training. There's not, I think, not so exciting. The more exciting will be when I try to use in a weight only training. So this means that I only keep an in a of the weights and then train with that. So I think I have this PR on there. So so the idea of this one is that we only keep a copy of the model, and I do the forward pass and backward pass and weight updates, everything with an in 8 weights. And because this is weight only, right, it means that in the forward pass, I still just dequantize it into BF16 and do normal BF16, more BF16 flash intention and so on. But the only difference is that I store the weights in a storage. So let me see. Okay, this one also represent this one, maybe this one. So this one I trained for a very long time, and sadly, right, it's still not as good as just doing BF16. So as you can see here, the loss that lower than the other two, it's the one with BF16. Yeah, so this is the baseline. And then the blue one will be the one that I'm using just in 8 weights. So there's still some gap. It's not good. So I don't think this can replace the BS16, but it just to show the idea how much you can push it. So even if with stochastic routing, you can do some learning. And then the green one is that I'm using in a weights and also a bit optimizer. So it's a bit worse at this point, but before that, it's still looking good. Yep. So this one is for the 400 something million parent. But if I change to 1 billion parent, I think the difference is much less. But I guess it's because when you have a bigger model, right, you have more capacity to quantize. Yeah. So I think that's just some interesting findings from it. So I think in general, like this one, although it looks cool, it's not too practical, I guess, because like I said, the first step you should try to quantize your optimizer state first because that's actually twice the size of your model. Yeah, but it just show how much we can push stochastic routing to do funny stuff here. Yep. So I just put down what I just said here in the slides. Okay, so we are moving on to the next one will be low bit mixed precision training. Um, so the difference compared to the one I just went over is that in this one we're still using FP32 weights, for example, but we will quantize both the weight and activation during the training to make use of high speed tensor cores. Remember in the weight only, right? For this one, we don't use low bit tensor cores yet. So basically, we just quantize the weight to save memory. The main goal of this one just to save memory. But for this one, the main goal is not to save memory because we still keep FP32 weights. But this one, the main goal is to speed up because we want to use low precision tensor cores. Okay, just let me drink water. I think I talk a lot in the short amount of time. Okay, so I put a table here like the speed of different tensor core with on different data types and to convince you why you should care about this. So one interesting thing that many of you might have not known is that for consumer GPUs, in a tensor core is actually 4 times faster than BF16. So it's not 2 times, it's actually 4 times. And this only for consumer GPU. Consumer GPU. So actually even the newest 9050 5090, I'm sorry, 5090. It's also 4 times faster than the F16. Yeah. And this is not the case for enterprise cards. For enterprise cards like A100 and H100, in A is still just 2 times faster. Yep. And those numbers are here. Yep. So I think this should be enough to convince yourself that if you want faster training, you should try to use even lower bits, lower than BF16. So there are problems with that, right? Because we can't just use low bit the right away. The biggest problem is because they have very different scale or range of values. For example, in A you have like just 1 up to 128, and then for FP8 you have only this much. So it's still not enough to cover like the whole range of the F16, for example. So the solution for this will be this thing in general we call it scale matrix multiplication. So it's like you factor out the scale in the activation matrix, you factor out the scale in the weight matrix, you do matrix multiplication in low precision, and then you add the scale back. So to illustrate, right? So for example, we have like tensor Y scaling. So this was like one of the first FPA training recipe. So we have this one here. Just imagine this is the activation tensor, and this one here is the weight tensor. So we can just factor out like one big scale here. So we have like one single value for the whole activation, and then one single value for the whole weight. And then we can just do normal FP8 matrix multiplication, get this one. And then once we have this, we just multiply back this one number and this one number. So very straightforward. This one will be a bit more complicated, but this actually what's all of the framework have been using for the in a post training quantization. So this actually happening like even before all of the LLM grades. I think like CNN models where we do in a CNN, it's also like this. So the idea is that for the activation matrix, right, we will quantize it per row. So for example, when you have this one row, like it will share one scale. And then for the weight matrix, actually, when we do it normally in PyTorch, right, the weight is transposed. So actually, we don't do A times D. It's actually A times D transpose. So actually, the weight is also row-wise scaling. But just if we just look at the picture of the matrix multiplication, right, it will become column-wise scaling. So why does this works, right? And then it works nicely with everything, right? It's because for matrix multiplication, for each of the output value, it's actually just a dot product between the two matrix, right? I put an arrow here, so it's easier to visualize. So to calculate this output value, basically you do a dot product between this and this one. So if we have one scale for this vector and then one scale for the other vector, then it's straightforward, right? So we just do a low bit map more for this with this one, and then we just scale for the output here. We use the scaling. And then we can do that the same thing for every other value in the output matrix. So this one, I call this the most simple way because basically we can just factor out the scaling and then we just put that back at the end. So there's no modification to the map mode in the loop, which is the loop that when we loop over this direction, when we do the dot product here. So this is like a kind of new slide I just put in compared to the previous talk I gave because everyone knows that this DeepSeek V3 paper. And what they did is a bit more complicated. Is that actually they break down this dimension here, so you don't have the ability to just do the scaling in the end. Because you see here, like this block is shared among these 4 elements, right? And then this one shared among the 2 elements. It means that when we, for example, we want to calculate this value, right? We have to go, we have to do map more between this block and this one, and then we get something. And then we do the scaling for that something. And then we have to move to the next one. So we have to do the map more between this and this one. But the problem is that we cannot add them directly into what we have so far because they require different scaling. So for example, this one, they will require scaling from this here. Let me see if I can just change to the pane. So this one, it requires scaling from this. And then this requires scaling from this one. So when we do the map mode, we cannot just keep accumulate to the same accumulator. So that's why I put here, we require a second accumulator. So this one is a bit more complicated, and that's why it's actually a bit slower than the other two, but it will give better accuracy. So that's why I think if you look at the DeepSeek V3, I don't remember, I saw the number somewhere, but you see that the speed up from FPA is not actually a lot. It's like, I think 1.2 or something. I can't remember how I remember that figure. I just look at the paper again, I can't find any reference to it. But yeah, that's why you can see that. But the good thing is that it's have better accuracy because you have like a smaller granularity of this quantization. Okay, so just this one just cover like and I think most of the popular scale matrix multiplication, the more typical ones. Okay, so going back to the more higher level about the low bit precision training. So mixed precision tool means that way is the FP32, right? And we will dynamically quantize A and B to low precision to do to use the low bit tensor cores. And if we just take a look at different D types and then different scaling strategy. So if we look at FP16, actually there is also some scaling, but the scaling is a bit different. It's you are using the same scaling in the backward pass. So if you are old enough to still remember when FP16 training was kind of popular back in the days. Yep. So in FP16, we don't do scaling in forward. We actually do scaling in the backward pass, and the scaling is the same for all of the operations. For BS16, there's no scaling, so that's why actually BS60 is kind of popular right now because we don't need the tricks for FP16 anymore. For FPA, the earlier FPA using tensor-wise scaling, and then the one that DeepSeek used, I showed just now, they're using block-wise scaling. And we have E8 here. So E8 here, so this one is more for the post-training quantization. And then one thing I want to mention that's kind of interesting is that before me, right, there's actually very few people, actually like no one write E8 training for PyTorch. I only saw a framework from Google. It's called AQT. But apart from that, I don't see any people discussing about using it like for training. So this card, okay. So that's what I did here. Actually, I did some experiments before that, and then okay, let me go to this PR. And then I put that in the torchao, so that's why it looks just in here in the mixed precision training. So okay, let's go to the results, I guess. So I did some. Okay, is this the long training? Okay, so this one is the long training that I did. So this one I did like, okay, if I look at 20,000 steps. So you see here when I do the in a mixed precision, at least for this setup, actually you see that it match exactly the same as BF16. And actually for BF16, there was a point that I got some instability. This one, I'm not sure why, maybe I just got unlucky. But the idea is that you see that it matched almost perfectly with BF16. Yep, and I get where's the speed up? Where do I speed up? Okay, I have the speed up here. So yeah, so the speed up is insane. So that's one. Oh, I didn't put percentage. Oh, 70% speed up, 70% speed up. So just to give you a recap, I think just now when I showed the table, they say that in eight on the consumer car is actually 4 times faster. So you see that here it's only 70% faster, so maybe not so good. But that's just the way it is because when we do this kind of thing, right, we have a lot of more overhead. We have to quantize the activation and the weight dynamically during training, and that adds up the overhead here. So we will never realize the max potential of the low bit tensor core. So but I think 70% speed up is really impressive already. And you see that the loss actually very similar. And the validation loss is actually better, but again, I think there's something weird about my run here with BF16. Yep, but otherwise looks everything looks very good. I also did more benchmark with different models. So I think this one is with torchao. Um Yeah, so the loss we see basically identical. There's some divergence, but not too much. And then back then, I think there's some problem with touch tools about how they handle the dynamic sequence length. So you didn't see good speed up, but if you have a better, if you do like something like token packing for LLM training, then actually you will see much better speed up here. The problem with that, I'm using I write a custom Triton kernel for this. I think this one I showed the Triton kernel. And because of this Triton kernel, right, it will auto tune based on the different shape of the matrix. And if you don't optimize your LLM fine tuning pipeline, right, it means that every time you get a different sequence, it will be you have very different sequence length, and then with every different sequence length value, it will rerun the auto tune. That's why it's not so good. Yeah, but if you do sequence packing, you can look it up later. Then you should see pretty much speed up here. Okay. Oh yeah. I think I talked too fast. That's why I got a lot of cough. So at this point, any one of you have questions?
I was curious, like, did you try anything with like vision workloads, and did you see? I mean, I know you have some experiments in the repository, but like, was it easier or harder with like vision? Like, this is mostly, I'm assuming, text, right? Like text only
So
models.
you're asking about the vision, like training vision models, right?
Yeah, yeah, and I think one comment you did make is that it's easier with larger models to use this kind of technique.
Right.
Yeah.
I
So
don't have like figures to show you right now, but I remember that I tried this to train some face recognition models. So just to give a brief overview, so to nowadays I think the best way to train face recognition model is still you have this huge data sets of a lot of faces, and then you train a basic model like CNN or like VIT on the classification objective, but you just classify whose face is this. So you just have a huge number of classes like hundred thousands number of classes because you have a lot of identities. So as you can see, that is something like a training a VIT on image classification. So I try on that one, and actually it's using in a mixed precision, and actually it gives kind of much worse performance compared to just BF16. I didn't spend too much time debugging what's happening there. Yeah, but yeah, just that's from my limited experience. Yep. So probably with vision there might be some challenges, but yeah, I think if I can get people get interested in it enough, then maybe we can get more data points from other people trying to use this for vision models.
Yeah, thanks. One other question is regarding the low bit optimizers. There is some discussion regarding the different moments of Adam being more sensitive. Did you have to account for that, or like did you do anything special there, or how would you approach in a low bit setting?
Usually, usually, I don't do with the algorithmic side because it's kind of much more complex. Usually, okay, what I did for the torchao is just basically I translate the original research code, which usually requires some custom CUDA kernel. I translate that so that it's only in pure PyTorch and rely on Torch compile to make it fast. Yeah. So in terms of like convergence, I just the research code. I don't usually research much into that.
Okay, yeah, I see. Yeah, thanks.
Okay, so
Uh,
I,
uh,
yes.
I had a quick query regarding Blackwell's FP6 and FP4. Did you like manage to try on that, or do you have plans to experiment with that stuff?
Um, right. I think that looks very exciting. I think one of the parts I put in the last slide is also about FP4, but sadly I don't have access to a Blackwell GPU. So if I buy myself a Blackwell GPU in the future, then I will probably play with it. But right now I don't have plans. Mostly because I don't have access to it. Yeah. Okay. Okay, so I think that's kind of like cover most of the things I want to talk about in this talk already. Other stuff is just like more of like random thoughts and open discussion. So, for example, just now I make a very clear distinction about like the weight only training, like innate weight only training, and then the in a mixed precision training. But why not combine both, right? Like why not we use in a way only, like we don't keep the FP32 weight, and we also use the in a matrix multiplication. Um, the problem is that there are in particular for in a because we're doing row wise scaling. One problem is that because the backward pass will be a bit problematic. So if we look at the math here, so this is the forward pass for the linear layer activation template weight transpose, right? And in the backward path, every the all of the matrix here will become transposed. So it means that, for example, if we look at this forward path, we will quantize W in the row-wise direction, right? But in the backward path, W will be quantized in the column direction. So that's problematic because, for example, if we keep the E8 weight in the we quantize it per row, but then later we also need to be quantized per column. Yep. So that's kind of not very compatible with what we are doing right now. Yeah, of course we can do for this thing like we can just dequantize and quantize it again. Yeah, but this will of course we add extra overhead and what did I put here? Oh right. So I think one interesting idea from here is that actually we can also use in a let's call it like dynamic in a memo, right? In other scenario, like for example, like Q LoRa. So in the Q LoRa, let me put back the diagram so it's clear. Maybe just go here. Q LoRa. So in the Q LoRa setting, you have two paths, right? You have to go through the base weight and then go through the LoRa weight. So when we go through the base weight, right, actually we can also do in a memo or FBA memo here just to speed things up. Yep. So I think the combination it's unlimited. It's just how creative you can get with different stuff you want to do. And oh right, there's one slide about BitNet. So I think BitNet get some attention last year. The idea of I won't talk too much about BitNet, but basically the idea is that the weight will be uh, quantized into these three possible values, and they use tensor-wise scaling, and then activation will be row-wise scaling to int8. So with the knowledge of this talk that I have been showing so far, I hope that you can realize that here it means that we can use int8 tensor cores, because this one is fit nicely into int8, and this one is already int8 here. So actually, we can speed up BitNet training significantly by using int8. Originally, they're using quantized aware training. So it means that even though they quantize away into these three values, right, they will be quantized into BF16 to do the MAPMO. It's the same as activation. Yep. So I think this also one of my the experiments I did. You can go to the PR, nothing too fancy. And yeah, so like I think it just to show you like the hardware is there. We should be able to identify opportunities to better utilize the hardware. Like for example, in this case, it's already everything is already perfectly nice for the using int8 tensor cores, and you just do it. And one interesting is that when we have distributed training like using FSDT, won't talk too much on this, but because we have like the weight in these three possible values, right, we can do a much very efficient two bit altogether. So it also reduces the combination cost between the GPUs when you have like very large distributed training settings. Yeah, so this one here, so give some more research papers about using low bit training. One thing I want to highlight, this one is about Jetfire. So actually this uses the same ideas as DeepSeek V3, but it's using int8. But if you look closely at the result, actually it's not that good in terms of the speed up. I think because their kernel is not very good. So maybe some of you, if you're interested, you can try even improve the int8 training further by writing better kernels out there. Because remember, let's go back to this diagram. On the consumer cards, right? FPA is only 2 times faster, but int8 is 4 times. Yep. So I think there's still a lot of interesting thing you can do with int8 because it just gives you better speed up. Yeah. So that's kind of the end of the talk here. So just kind of give some conclusion here. So if you want faster training, just basically try to use int8 and FPA. A lot of works have been done for FPA here. So if your GPU support it, you should try to do it. I think not many people try to look into int8 anymore, but I think that's something interesting and good to do because, like I said, on consumer card, it's much faster than FPA. Yep, and thanks to the Torch compile and Triton, right, it's actually quite straightforward to make things fast. So many of the things that I have showed earlier, most of the thing it's done by Torch compile, and in very rare cases, I need to write a Triton kernel. So for example, I only need to write a Triton kernel for the scale matrix multiplication to do the fusion of the scaling in the Matmo epilogue. But otherwise, most of the stuff will be handled by Torch compile, and it gives you a very pleasant experience. Yep, and stochastic routing, I think, is a very neat idea, and maybe you can push it to many other stuff. For example, like low bit or reduce. So I don't have access to any distributed system, so not sure what's the standard right now. But imagine, for example, when we do a training, and then usually the final state is like or reduce the gradients to get the gradients on each of the GPUs, right? I think most of the time the minimum you have to do is using BF16 to do the or reduce operation. But if you can also quantize it and maybe use some kind of stochastic routing to help with the error correction, then you can significantly speed up the distributed communication latency, and that will speed up training. Yeah, so other idea exploits that. One thing that we can even go down even more low bit, right? Like someone mentioned about FP4. So I think this will be like kind of the hot topic people will try to do right now. I think someone said a paper on FP4 training, right? From Microsoft, I think. Yeah, I think that one it was doing in simulation, so it's a bit different. And I think they use tensor-wise scaling. I think they didn't use like the kind of the blockwise scaling like from the MXC type. So there's still a lot of potential room for discovery. I put in 4 tensor cores here, but sadly, NVIDIA stopped supporting in 4 tensor cores from Blackwell onwards. So if you have like 4090 or something, that will be the last generation of GPU that support in 4. And sadly, it's not very simple to do in 4 and FP4 yet. I think Triton is adding support for FP4. I haven't been following, but I don't know. So, for example, I also tried to use it in 4 tensor cores and have to use Cutlass, which is not a very straightforward library to use. So basically C++, and you have to do a very specific way to do what they want you to do to get things there. Yep. So I got in 4 tensor cores working, but I haven't tried to like put that inside a training stack game. But someone can try that. So I think that's also interesting because in 4 it will be even faster in 8. I think that will be all for what I have to share. So maybe I just stay back a few minutes if any of you have questions. Or we can just discuss anything.